Okay, in this video we're going to look at a new type of isomerism called optical isomerism, and optical isomers are non-superimposable mirror images. Non-superimposable, meaning not being able to be placed directly on top of each other, mirror images. So if you want an example that you can look at in front of you right now, if you put your hands together, they are, to all intents and purposes, mirror images of one another, but if you try to put your left hand on top of your right hand, your thumb lines up with your little finger, not with your thumb. Non-superimposable mirror images. Now, for an organic compound to exhibit optical isomerism, it must contain a carbon that is bonded to 4 different groups. So each thing attached to that carbon must be unique. And this asymmetric, so non-symmetrical carbon atom is called a chiral carbon. So if I give you an example, I can draw a carbon in a structure. So I'm just going to draw for you a simple structure of an amino acid for this example. And I'm going to draw out alanine. Now, alanine structure can be found on your data sheet. Alanine has a methyl group and a hydrogen attached to the amino acid structure. Looks like this. Now this carbon in the centre here would be classed as a chiral carbon because each of the things attached to it are unique. So we've got a hydrogen, that's group number 1. We've got a COO group, a carboxylic acid group, that's group number 2. We have a methyl, that's group number 3. And we also have an amine group, that's group number 4. So 4 unique groups. That makes this a chiral carbon. Optical isomers are sometimes, as well as being called optical isomers, referred to as enantiomers. That's another word you might hear, come across and should be familiar with, enantiomers. Optical isomers or enantiomers differ only in one way. They differ in their effect on plane polarised light. Plane polarised light is light that has been polarised into one particular direction. So your sunglasses may do this for you. You may have done this with a physics experiment at school where you make the light just travel through a slit in one direction. Optical isomers will be able to rotate, and it's important that you use that word, rotate the light by an equal amount as each other. So one of the optical isomers will rotate it perhaps 30 degrees anti-clockwise, but the other one will rotate it 30 degrees in the opposite direction. So they rotate light by an equal amount but in opposite directions, and that is how we can tell them apart. So let's have a look at how we could identify and draw them. So first thing we have to decide is, does it have optical isomerism? So draw out the structure of pentan-2-ol. Pause the video and draw out the structure of pentan-2-ol. So I've drawn it out. I've used mostly displayed formula, though do be careful, I haven't displayed the alcohol group fully. Drawn out the structure of pent, meaning 5, so I've got 5 carbons, and on the second carbon I have drawn an alcohol group, pentan-2-ol. Now I want to go down here and see if I can find a carbon with 4 different groups. I'm going to start on the left. The very carbon on the very left, this one here, has got 3 hydrogens, so that's not 4 different things. The second carbon has got 2 hydrogens, so there's not going to be 4 different things there. The next one's got 2 hydrogens, so there's not going to be 4 different things there. The next one, when I hit that alcohol carbon, I can see that there are some different groups. So I'm going to see if I've got 4 different things. I've got the hydroxyl group, the alcohol bit. I've got a hydrogen atom. I'm just going to change the colour of that highlighting for you so that you can see it as 4 different groups. There's group number 2. I've got a methyl group, so that's my third group, methyl group. And then my last group is all of this, the whole thing. Again, I need to change that colour of highlighting for you. I'm just going to change that to a different colour so you can see it unique. All of this is a propyl group. The whole lot is my fourth group. So I have 4 different groups. I've got group number 1, an alcohol, group number 2, a hydrogen, group number 3, a methyl, and group number 4, a CH2, CH2, CH3, a propyl. Just match those up. So I've got group number 1 was our alcohol, group number 2, our hydrogen, group number 3, our methyl, group number 4, our propyl group. 4 different groups. That makes this carbon here a chiral carbon, and it asks me to mark it with an asterisk. Now, in order to show non-superimposable mirror images, you have to show the tetrahedral arrangement. You can't do it without showing the tetrahedral arrangement. So you need to practice drawing your tetrahedral shape. If you look at the page, we've drawn out 2 tetrahedral shapes for you. We're looking for this 109.5 angle here that makes it appear tetrahedral, and then the wedge that shows the bond coming down and out of the board, and the dashed line that shows the bond going down behind the board. Right, so what we need to do is arrange the 4 groups. So remember I had those 4 groups, the first of which we had an alcohol group. I'm going to put that here. And then we had a hydrogen. And then group number 3 was a methyl. And group number 4 was that big propyl group. Now, my little top tip to you is always put the biggest group on the top stick, because when we have to draw our mirror image shortly, it's easier to draw things on that very top stick because you don't have to reflect arrangements. So when we draw the mirror image, we're reflecting position, we're not reflecting our writing. So we don't want to see backwards letters, we still need to see carbons and hydrogens written properly. So the reason I put my nice big group at the top was so that I could easily write it over here with good connectivity without making any mistakes. I do have to reflect the position of the alcohol group, so it's in the mirror, it would be closest to the mirror, and here the hydrogen would be closest to the mirror, and the methyl group is furthest away. So I've drawn a mirror image of my original structure. These would be my 2 optical isomers. They are different because you cannot pick one up and put it on the other without all the groups lining up. So I want you to use your notes pack now and have a go, and then pause the video, come back in a few minutes when you've had a look at them and see if you can decide which one of each of these 2 structures has optical isomers, and then when you've chosen that one, draw the 2 optical isomers as non-superimposable mirror images. So pause the video and have a go at this section. So our first example, we've got 2-chloropropane versus 2-chlorobutane. You can see that in 2-chloropropane there are no chiral carbons. You could be tempted to think the middle carbon is chiral, but it has got a chlorine and a hydrogen, but either side it's got the same group, both sides is a methyl. When you look at 2-chlorobutane on the other hand, this carbon here does have 4 different groups, and we can see that we've got a methyl group, a hydrogen, just change the colour of that highlighting for you, a chlorine, and then final one, we've got this ethyl group. All of this is an ethyl group, 4 different groups attached to that carbon. So for 2-chlorobutane we can draw non-superimposable mirror images. So I'm just going to draw that in quickly for you so you can see how I would go about drawing it. So the 109.5 bond angle between the 2 bonds in the plane, and then I'm going to put the biggest group here. Remember, that's my little top tip. Put the biggest group here, so that's the ethyl group. Put the smallest groups here by the mirror. Okay, and then anything else over here. So I've got CH3. I can draw in a little mirror, and then I'm going to reflect everything. So it's going to reflect the positions of the bonds and the positions of the groups. So have a go at the rest of the examples on these pages and check back in a second when you've paused the video and had a go at whether you've got your answers right. So for this second example, we've got butan-1-ol versus butan-2-ol. Only butan-2-ol has a chiral centre. So I've drawn butan-2-ol and its mirror image. Now, don't worry if your groups aren't in the same places, as long as in your mirror image, so in your version that's in the mirror, you've put them in the reflected position. There is no reason that you can't change the position in one of them as long as you reflect it in your second one. This is not the only right answer. There we go, we can look at our second set of examples. Propanoic acid doesn't have a chiral centre, but 2-hydroxypropanoic acid does. And again, I've drawn my mirror image isomers. And then for my final example, you can see I've drawn the two structures out, and the one on the right has a chiral centre, put that in with our asterisks, and then I've drawn my 2 mirror image isomers. It'll be worth you going away and finding some questions on this to review and have another go at.